Light is everywhere, right now, hitting your eyes, bouncing off every surface in the room, carrying information from every object you can see directly into your brain. And nobody knows what it is, not approximately, not we're still working out the details. Fundamentally, deeply, after 300 years of the best physics the human mind has ever produced, we cannot tell you what light actually is. We know what it does with extraordinary precision. We can calculate it to 1 part in a trillion. We've built lasers, fiber optics, solar panels, the entire technology of vision, all of it built on top of something we haven't understood. I find that remarkable, and I want to show you why. Because every time physics gets close to pinning light down, it finds something that shouldn't be possible. Something that works perfectly in the equations and makes no sense whatsoever as a picture of reality. The closer you look, the stranger it gets. And the strangeness isn't a gap waiting to be filled, it's the answer. For most of the 1800s, the question seemed settled. Thomas Young fired light through 2 narrow slits in 1801 and looked at what appeared on a screen behind them. If light were made of particles, you'd expect 2 bright bands, one behind each slit. What he got was an interference pattern. Dozens of alternating bright and dark stripes spread across the screen. Interference is what waves do. When 2 waves meet, they either reinforce each other where their peaks align or cancel each other where a peak meets a trough. Water waves do this, sound waves do this, and now light was doing it too. Particles don't interfere. They hit, they scatter, they don't cancel each other out. The interference pattern was unambiguous. Light is a wave. James Clerk Maxwell closed the case in 1865. He worked out the complete mathematical description of electricity and magnetism. 4 equations, unified, elegant, complete. And inside those equations, he found something nobody had put there: a self-sustaining oscillation. A changing electric field generates a changing magnetic field, which generates a changing electric field, which propagates forward through space at a speed that fell directly out of the fundamental constants of electricity and magnetism. That speed was the speed of light, exactly, not approximately. It emerged from the math without anyone asking it to. Light, Maxwell showed, is an electromagnetic wave. Electric and magnetic fields oscillating together, each one generating the other, rolling forward through space. It wasn't just a model, it was a derivation. Light, electricity, magnetism. One thing. The greatest unification in 19th century physics. By 1900, the nature of light was considered solved. Then the photoelectric effect ruined everything. Shine light on certain metals and electrons get knocked off the surface. That was known. What was strange was the pattern. If light is a wave, more intensity means more energy in the wave. So brighter light should knock off more energetic electrons. And eventually any color of light, bright enough, should work. That's not what happens. Below a certain frequency of light, no electrons, no matter how bright. Above that frequency, electrons come off instantly, even at very low brightness. And the energy of each electron depends only on the color of light, not how bright it is. This is impossible for a wave. A wave's energy depends on its amplitude, its brightness. The frequency shouldn't matter the way it did. Something was wrong with the wave picture. Einstein solved it in 1905. Light comes in discrete packets, quanta. Each packet carries energy proportional to its frequency. One packet either has enough energy to knock an electron free, or it doesn't. No packet below the threshold does anything, no matter how many of them there are. One packet above the threshold works immediately. We call these packets photons. Einstein won the Nobel Prize for this. Not for relativity, for the photon. Now hold both facts at once. Young's experiment proves light is a wave. Einstein's explanation of the photoelectric effect proves light is made of particles. These 2 descriptions are mutually exclusive in classical physics. A wave is spread out, extended through space, interfering with itself. A particle is localized, a discrete thing in one place at one time. Light is both, and here's what that actually means in practice. Fire photons through Young's double-slit, one at a time. A single photon, no other photon to interfere with. It hits the screen at one point, like a particle, then another, each one a dot. It looks random. Keep going. Thousands of photons, each one arriving alone, and the pattern that builds up is the interference pattern. The same alternating fringes Young got, from particles, arriving one at a time, with nothing to interfere with. A single photon, alone, goes through both slits simultaneously and interferes with itself. Now put a detector at the slits to find out which one the photon actually went through. The interference pattern vanishes, completely, instantly. You get two bands, one behind each slit, exactly what particles would produce, exactly what you'd expect if each photon went through one slit or the other. Remove the detector. Fringes return. The photon behaves like a wave when you don't look at its path. It behaves like a particle when you do. And this is not the detector disturbing the photon in some mechanical way you could engineer around. The determining factor is whether information about which path exists anywhere in the universe, not whether you personally checked, whether the information is available, in principle, to anything. I call this the only real mystery of quantum mechanics. I meant it. Every quantum paradox you've ever heard of is this experiment in some form. Now, here's something that was bothering people even before the quantum weirdness arrived. Maxwell's wave needed a medium. Every wave anyone had ever encountered was a disturbance in something. Water waves disturb water. Sound waves compress air. A wave is a pattern of disturbance propagating through a medium. If light is a wave, it needs something to wave in. Victorian physicists called it the luminiferous ether, a substance filling all of space, invisible, undetectable except by its effect on light. It had to exist. The wave model required it. In 1887, Albert Michelson and Edward Morley built an extraordinarily precise interferometer to detect it. The logic was simple. If the Earth moves through the ether, light traveling in the direction of Earth's motion should travel at a slightly different speed than light traveling perpendicular to it, like swimming with a current versus across it. Measure both, compare, find the difference. No difference. None. Within any detectable margin. They tried it at different times of year, with Earth moving in different directions through its orbit. Still nothing. The ether wasn't there. This was the most famous null result in physics. If there's no medium, light travels at the same speed for every observer, regardless of their motion, which is exactly what Einstein took as the foundation of special relativity. But it left a raw wound. If there's no medium, what's waving? Maxwell's equations describe electric and magnetic fields oscillating through space. Those fields are real. They deflect compass needles, they accelerate charges, they push and pull on matter. But what are they made of? Nothing. They're properties of space itself. The capacity of empty space to have a value at every point. The light wave propagates not through a substance, but through the ability of nothingness to be disturbed. That's the honest description. A disturbance in nothing, propagating through the capacity of empty space to have field values. Technically correct, philosophically vertiginous. And then there's the speed. Light travels at 299,792,458 meters per second. That's not just its speed, it's a constant of the universe, the same for every observer in every reference frame, regardless of their motion. In ordinary experience, speeds add. You're on a train moving at 60 miles per hour, you throw a ball forward at 10, someone on the ground sees the ball at 70. Simple, obvious. Now you're moving toward a light source at half the speed of light. You measure the speed of the incoming light. You get c, not 1.5 c, just c. Move away at half the speed of light, measure the same light beam, still c, exactly. Einstein didn't explain why this is true. He took it as a postulate and asked, if this is just how the universe is, what follows? What follows is special relativity, time dilation, length contraction, the equivalence of mass and energy, the relativity of simultaneity. The entire structure falls out of taking c seriously. But why is c constant? Why does it have the value it has and not some other value? Maxwell's equations predict a specific electromagnetic wave speed from the fundamental constants of electricity and magnetism. Those constants are what they are. We measure them. We don't derive them from anything more fundamental. The speed of light is not explained, it's found. It shows up in Maxwell's equations, in the Lorentz transformation, in E equals mc squared, as the boundary of the light cone in space-time. It's not just the speed of light, it's the speed of causality itself, the maximum rate at which any influence can propagate through the universe. We measured it. We used it. We don't know why it is what it is. Now here's something that rarely gets said directly. From the photon's own reference frame, if a photon could have a reference frame, it experiences zero time between emission and absorption. Special relativity tells us that time passes more slowly for faster-moving objects. At the speed of light, time stops. The space-time interval for a photon, the relativistic measure of the distance between two events, is exactly zero. A photon emitted from a star 8 minutes away and absorbed in your eye has in its own frame traveled zero distance in zero time. For the photon, emission and absorption are the same moment. The journey we perceive as 8 minutes of light travel is from the light's frame instantaneous. Not fast, instantaneous. No duration, no traversal. Light connects 2 points in space-time without experiencing the space between them. The thing that carries information across the universe experiences none of the journey. I don't know what to do with that. Mathematically, it's clean. As a picture of what's happening, I find it genuinely bewildering. Now, let me tell you about the theory that describes all of this with extraordinary accuracy, and why it still doesn't give you a picture. Quantum electrodynamics, QED, is the theory of how light and matter interact at the quantum level. It is the most precisely tested theory in the history of science. Its predictions agree with experiment to 1 part in a trillion. If you used QED to calculate the distance from New York to Los Angeles, and your answer was off by a human hair, you'd be doing worse than QED does. I helped build this theory. I won the Nobel Prize for it. And I'll tell you honestly, I don't know what it's describing. QED says a photon traveling from point A to point B doesn't take one path. It takes all paths simultaneously. Every possible trajectory, straight lines, wild curves, paths that loop back in time. The photon's propagation is calculated as a sum over all of them, each weighted by a probability amplitude. Most of them cancel each other out. The paths that reinforce each other are what we observe. This procedure works perfectly, every time. It gives the right number to 1 part in a trillion. But what process is it summarizing? What is actually happening when the photon travels? The calculation doesn't say. It gives you the right answer by summing over everything and watching what survives. The everything isn't a description of reality. It's a procedure that produces correct predictions. Whether it's telling you what's really happening is a separate question, and the answer is, we don't know. There are also virtual photons. In QED, forces between charged particles are described as exchanges of photons, but these are virtual photons, meaning they exist only in the intermediate steps of the calculation. They can have energies and momenta that violate what real photons are allowed to have. They can't be directly detected. They're mathematical objects that appear in the perturbation expansion and produce the right answers for how magnets push each other, how electrons repel. What is a virtual photon physically? What's actually happening in the space between 2 magnets when they push apart? The calculation works. The picture, nobody has one. I think I can safely say that nobody understands quantum mechanics. I don't mean nobody has learned enough. I mean the theory gives correct answers and does not give a coherent picture of what's actually happening. Those are different problems, and only one of them is solved. There's one more layer I want to add, because it reveals something about light that doesn't fit into either waves or particles. Photons have spin, not spin like a top rotating on an axis. There's no axis, no physical rotation. Spin in quantum mechanics is an intrinsic angular momentum that has no classical picture. It's a property photons have the way they have energy, built in, fundamental, not derived from any motion. Photons have spin 1. Electrons have spin 1/2. The difference matters. It determines how particles combine, which statistics they obey, how they behave in quantum fields. Photon spin shows up as polarization. The 2 polarization states of light correspond to the 2 spin states of the photon. Circular polarization is the photon in a definite spin state. Linear polarization is a quantum superposition of spin states. This is why polarized sunglasses work. This is why 3D cinema works. Real engineering, in your hands right now, built on the intrinsic angular momentum of a particle that isn't rotating. Why does a massless particle that isn't spinning have angular momentum? Because spin is a consequence of how particles transform under the symmetries of space-time, specifically the Lorentz group, the mathematical structure that describes rotations and boosts in special relativity. The spin 1 of the photon follows from the fact that light is described by a spin 1 field in a Lorentz invariant theory. The symmetries of space-time determine which spin values are possible. We don't know why space-time has those symmetries rather than different ones. We're back at bedrock again. And light bends around massive objects. Einstein's general relativity predicts it. Mass curves space-time, and everything, including light, follows the curvature. In 1919, Arthur Eddington measured the positions of stars near the sun during a solar eclipse. Their positions were shifted from where they should have been, by exactly the amount Einstein predicted. Not approximately, exactly. We now use gravitational lensing as an observational tool. Massive galaxy clusters bend the light from objects behind them, producing arcs and multiple images and rings. We use the bending of light to map dark matter, matter we can't see directly, but whose gravitational effect on light we can measure with precision. Here's what should bother you. Photons are massless. Classical gravity acts on mass. Why does a massless particle respond to gravity at all? In general relativity, gravity isn't a force that acts on mass. It's the curvature of space-time. Everything travels through space-time. Everything follows geodesics, the straightest possible paths through curved space. A photon's path curves around a massive object not because gravity pulls it, but because the space it's traveling through is curved. But photons carry energy, and energy gravitates. So light bends space-time by a tiny but non-zero amount. Two beams of light traveling toward each other attract each other gravitationally. Two beams traveling in the same direction don't. Light is not just a traveler through space-time's geometry. It's a participant in it. So let's be clear about where we actually are. Light behaves as a wave. The interference pattern is real. Light behaves as a particle. The photoelectric effect is real. Which behavior appears depends on how you interact with it, and the determining factor is whether path information exists anywhere in the universe, not whether any particular observer checked. Light has no medium. It propagates through the capacity of empty space to have field values, through nothing. The speed of light is the same for every observer, always, exactly. We don't know why. It's built into the structure of space-time, deeper than any explanation we currently have. From a photon's own frame, every journey is instantaneous. Emission and absorption are the same event. The thing that illuminates the universe experiences none of the illumination. QED describes all of this with 1 part in a trillion accuracy. QED does not tell you what's actually happening. It gives correct answers through a procedure summing over all paths that has no classical analog and no clear physical interpretation. Virtual photons appear in the calculation of forces. Nobody knows what they are physically. Light has intrinsic angular momentum from symmetries of space-time we don't derive from anything more fundamental. Light curves space-time and is curved by it. What is light? I've spent my career calculating it, using it, building theories around it, and I can tell you, we know what it does. We cannot tell you what it is. And here's what I find beautiful about that. Genuinely beautiful, not consolation prize beautiful. Light has been in the universe since the first moments after the Big Bang. It connects everything, stars to eyes, the distant past to the present, every source to every observer. It carries every signal, every image, every piece of information that ever crossed space. It makes vision possible, and therefore thought possible, and therefore the asking of this question possible. And it does all of that while being something we can't quite pin down, something that refuses to sit still in either of the categories we have for it, something that travels across the universe without experiencing the journey. The thing that shows us everything turns out to be the hardest thing to see. I've been working with light my entire career. I still don't know what it is. And I've decided that's not a failure. It's an invitation. Every time I think I've got a corner of it, it slips into something stranger and more interesting. That's not physics falling short. That's the universe being deeper than our descriptions of it, which means there's still something real left to find. And that, honestly, is the best possible news.